Bismillahirrahmanirrahim. I am Dr. Muhammad Adnan, working as Assistant Professor in the Department of Physics, Cohort University of Science and Technology. I welcome you to the course PHY 103 Waves and Oscillations. Today it is the 11th lecture of this course and the topic is speed of a traveling wave. First, I will give the learning objectives. At the end of this presentation, the student will know how to calculate the speed of a traveling wave, and also they will be able to calculate the linear density mu of a uniform string in terms of total mass and total length. Also, they will be able to find out the relation for the speed v in terms of the tension and the density. In this course, we are following the book Fundamentals of Physics by Holliday, Resnick and Walker, 10th edition. Some of the illustrations are taken from this book. We will start with the speed of a traveling wave. In our previous lecture, we have discussed that how one can describe a traveling wave by a sine function, where this is the displacement along the transverse direction, this ym is the maximum amplitude, this is the function psi which represent the shape of the wave, and this kx minus omega t is the phase of that function, such that k represent the angular wave number and omega represent the angular frequency. Now, to calculate the speed of this sine wave traveling in the positive x direction with the velocity v, so this is just a two snapshot taken at two different times. For example, the first one, the green one, is taken with t is equal to 0, and after an interval delta t, there one took another snapshot such that random position, this is just a mark on the first string a, such that transverse displacement is the same while taking the second snapshot. So by condition, if point A retains its displacement as it moves, the phase in the above equation gives it that the displacement must remain constant. For example, the first one represented by y1 equal to y1m sine of kx minus omega t for the first one, and then for another y2 is equal to y2m, since the amplitudes are the same and the function is the same sign, so it means that kx minus omega t, that is the phase, is the same, that is the phase is constant, so that between those two snapshot, this kx minus omega t is constant. That's why the amplitude is the same. So if one calculate the velocity or the speed of that traveling wave, we need to differentiate this equation with respect to time, such that this k, which is the angular wave number, into dx by dt minus omega, and then by definition dx by dt is velocity, and that will be equal to omega by k. So that will be the speed of a traveling wave. In our previous lecture, we have discussed that this omega is 2 pi over t and this k is 2 pi over lambda. So using those expressions, one can obtain the well-known equation for this speed of a wave, that is v is equal to lambda times f. F is the frequency, lambda is the wavelength. Now, from this expression, one can say that this velocity, the speed is equal to lambda, that is one complete cycle, the distance uh, over one complete orbit. Now if that if that sine wave is moving towards the negative x direction, so that one can represent that uh, wave by y equal to ym sine of kx plus omega t. In our previous lecture we have discussed that how to change the minus sign to plus sign while the uh, the wave is traveling to the opposite direction. And under the same condition, that is, the second snapshot is taken after delta t such that a spot is at the same amplitude, so that kx plus omega t now, which is the phase, is a constant. So again, working out that dx over dt, and that will be minus omega kx. This minus sign now shows that the wave is indeed moving towards the negative x direction. Here one can say that to make this kx minus omega t constant, so if t is increasing, it means x will also increase such that to compensate that change. But here t increasing, x must decrease, so that the wave is traveling towards the negative x direction. For any arbitrary shape, the wave representation will be like this, as we have discussed in our previous lecture, where h represent any function and this kx plus minus omega t representing the phase, such that this plus and minus sign shows in which direction the wave is traveling relative to the positive x direction. Now, so one can say that the speed of a wave is lambda times f. So now we'll be discussing the wave speed on a stretched string. So on a previous slide, we have seen that the wave speed depends upon the lambda and f. But actually, the wave speed is set by the properties of the medium, that is, the mass and elasticity, which determines how fast the wave can travel. Now, if a wave is to travel through a medium such as water, air, steel, as we have discussed in the first lecture, it must cause the particle of that medium to oscillate as it passes, right? Which requires both mass for kinetic energy and elasticity for the potential energy. So basically, the wave speed is determined by the properties of the medium, as we will discuss now. This is just a random transfer wave on a stretched spring. Now we can discuss the wave speed in two ways. The first one is the dimensional analysis, and the second one will be through the Newton second law. So the first one is that this wave speed is proportional to the tension in the string, that is, how much tension is there in the string, and also it depends upon the mass, and that mass dependency comes through this mu, because we have a rope of length L, say, and mass m, so then this linear density will be mass per unit length. So having proportionality of A and B. Now if one remove this sign of proportionality, so that there will be a constant. Now we know that velocity is length over time, c, and then tau is having tension, this is a force, so force is ma, so this is m, and then a is meter per second square, so that there will be length and then will be t minus 2 time and then minus 2, and then this star is having proportionality a, so that we will be LA t to the power minus 2a, and then we will be having uh, the dimension of mu, which is mass per unit length, so that mass times power b, and then length will be minus 1, and that will be minus b. So finding out these a and b, which comes out to be 1 over 2 and minus 1 over 2. A is 1 over 2 and b is minus 1 over 2. So that if we put this a and b here, so that the speed will be having proportional to the tension in the string, and also it is inversely proportional to the mass density, where the c is a dimensionless constant, so that it cannot be determined with a dimensional analysis. So the c is one that one can see on the second method, that this c is actually 1. So the speed of a wave through a stretched string is proportional to the tension, and also it is proportional to the uh, inertial factor, so that the speed of a traveling wave is determined by the medium properties, as we have discussed. Now the second approach is to uh, use the Newton's second law or the Newtonian mechanics. For that to understand, we have a portion of a sine wave, for example. This is just a small piece. Now this look quite big, but actually this is a small piece. Now a small string element of length delta L, right? Within the pulse is an arc of circle of radius r, and subtending an angle 2 theta at the center of the circle. Now, considering this pulse, which is taken from a string, and this wave is moving from left to right. The wave is moving from left to right, and for convenience to find out the speed, we choose a reference frame in which the pulse remains stationary. That is, we are observing the speed of this arc length from a co-moving frame with the wave. That is, we are sitting on a wave which is traveling towards the right side. Now, as we know that in the first lecture, that these transverse waves, the elements of the medium is just oscillating. They are not moving from one place to the other. So if one sees the wave is traveling towards the right and we are looking at this portion, so it will be like this portion is moving towards the left side instead of the right side, if you are looking uh, from a frame of the wave, so that the string appears to move past us from the right, and it will be like moving towards the left. This pulse will be like moving towards the left. Now we have taken that this portion is delta L, which is very small. It makes an angle theta such that the total angle of this arc is 2 theta. The radius of this arc is r. From a force with a magnitude equal to the tension in the string pulls tangentially on this element at each side. right? As I told you that the speed is proportional to the tension in the string. So this tension will sweep this wave on both sides. Now, if this is theta, so this will be theta, that is, this will be ta, the tension times cos theta, and this will be again tension times cos theta, while these will be the vertical components, the tension times sine thetas, which we have shown here. So these two components will be cancelled out, and the sine component of this tension will adds up, and that will be radially inward, that is, this portion of the 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 arc length will be having a force that will be equal to 2 times the tension tension times the sine of theta. That is, there will be a radially inward force that will move this the arc back towards the center of this circle. So as I told you, the horizontal component of this force is cancelled, but the vertical component add to form a radially restoring force. Now that force will be equal to 2 times the tension times sine theta, and as I told you that this is a very small uh, arc of length delta L, so that these thetas are very small, so that sine theta is approximately equal to theta, so that we are left with approximately ta times 2 theta. Now this 2 theta, which is the angular displacement, as we know from the circular motion that the arc length delta, generally it is written as s is equal to r theta. So from there we have theta is equal to 2 theta, and then that will be the arc length. Instead of s we have delta L, so s is equal to r times 2 theta, so that 2 theta will be the arc times the radius. So this is that force which actually push this element of the transverse the element of the the string at this position towards the equilibrium. Now, since mu is the linear mass density of the string, as I told you, that string is having mass density mu, which is defined as mass per unit length. Delta m is the mass of the small element. Let's say this length delta L possesses mass delta m, so that delta m, according to this definition, mu is delta m over delta L. So one can write this delta m as mu times delta L. The acceleration is v square over r, the centripetal acceleration, and that one can write the force, as I told you from your book, that this derivation is based on the Newton's second law. So this is like force is equal to mass time acceleration. The force F is equal to tau delta L over r, and then we have mass, which is mu times delta L, and then acceleration v square over r. Another way to look at this expression is that this force, which is the centripetal force equal to tau delta L over r, and that is generally equal to mv square over r, where m is this and acceleration is v square over r. So we are just equating the magnitude of the centripetal force, which is in this situation equal to the 2 times tension times sine theta. That comes out to be in measurable quantities tau times delta L over r, and m can be calculated by this definition of mu, so that it comes out to be this thing. Now, if one solve this expression such that these delta L will be cancelled out, these R will be cancelled out, and again we are getting the, the speed of a wave on a stretch string as under the root of over mu. That is, it is proportional to the tension in the string, and also it is proportional to the mass density. Now we will be solving a numerical problem on this particular situation. This problem is taken from your course book, chapter number 16 and problem number 14. The book is Fundamentals of Physics. Now, in this problem, the equation for a transverse wave is given. Y is equal to, generally we know that y is equal to ym sine of kx minus omega t. So the information are given. The tension in the string is given as 15 Newton. We need to find out what is the speed of that wave, and also we need to find out the linear density of this string in grams per meter. So we'll start with the wave representation, the general form for a sine wave. So if one compare the given information with this form, one can obtain that the amplitude is 2 millimeter. The angular wave number is 20 per meter, and the angular frequency is 600 radian per second. So these are information one can find out by comparing the two forms. Now first we need to find out the speed. So we know that the speed is omega over k, and omega is 600 and k is 20, so that this v will be equal to 30 meter per second. The second, to find out the mu, the mass density, where tension is given, so we know that the speed is under the root tau over mu. We need to find out this mu. The speed is 30 and this tension is 15 Newton. So rearranging this expression, one can have this mu in terms of gram per meter. By putting the values, one can find out that mu to be 617 gram per meter. Now, from your course book, after the problem number 14, you need to solve these 6 problems, 15, 16, 17 up to 21. These are based on the speed of a traveling wave. So you need to solve this problem. And with this, I thank you for your time.